All right, guys. So I'm going to move through section 4 as quickly as I can. There is a lot to it, so I apologize if at some points it feels like I'm going pretty fast. Just remember, you can always go backward then forwards as far as this lecture is concerned. So this section is going to cover these phase changes, and we're going to talk in depth about freezing. We're going to talk about melting. We're going to talk about boiling. We're going to look at a couple of different things, phase diagrams, vapor pressure curves in this section specifically. All of this stuff you've actually already answered questions on and you've already read. So I'm going to go through quickly, and I'm going to hit the points I really want to make sure we understand, because there were some misconceptions that I think we really just didn't understand. Okay, and just to start off, we're going to look at a solid, a liquid, a gas. We're going to be analyzing the changes from one to the other, or from another to a different one. All right, so we're going to be focusing on how do changes occur. And just a quickly reminder, solids are highly ordered on that far left. Liquids are going to be more spread apart. The molecules are able to move past each other. Gases are going to be very far apart. Remember, most of the space of a gas is empty space, with particles just kind of all over the place, and they're moving fastest in our gas phase, slowest in our solid phase. All right, so to start off, we have to talk about what this term phase means. It's just a word that describes the part of a system that is in a specific composition and has certain properties. So for instance, a gas, we know the particles are far apart, they're moving really fast, it's typically a high temperature compared to any other phase, and there are a bunch of other properties we've talked about before this section of this chapter. The next thing to discuss is just, we're going to be seeing randomly throughout this lecture phase changes and the names of those phase changes. So condensation is one. We will wrap up this section with a diagram that gives you all of the phases, that goes from any phase to any other phase you're interested in. And then I do want to remind you of this idea of a vapor, and vapors only exist when there is a liquid and a solid phase present at the same time, because a vapor is considered a gas that's actually in contact with a solid or a liquid. So a gas has to be present, and so does either a liquid or a solid at the same time for us to call something a vapor. And then the last thing on this particular slide is equilibrium. This is a huge concept in this chapter. Moving forward from here, we're going to talk about equilibrium a lot, just because equilibrium is a condition where we change our idea of a chemical equation, creating two products, and just it's done, right? We go from one state to a new state, and when we're in that new state, we see that's the end, right? We go from, say, maybe two reactants to two products, and those two products, once they're made, the reaction has been completed. Not the case in equilibrium. In fact, in equilibrium, what happens is we see the forward reaction to create our products is going to be happening at the same rate of our reverse reaction to create our reactants. So those things are equilibrium. Specifically, we're going to discuss at the point of closed containers right now. So we're going to focus on closed systems or containers. A closed system is just kind of a fancy term for anything that is controlled in a high order or a high manner. So in other words, if we take our Erlenmeyer and we put a stopper in it, we have closed the system and we have stopped the reaction from escaping that particular area. So think of a closed system like a closed container. And what we're going to see is that if we have a liquid in there, that at some point we may see a rate of condensation is going to equal the rate of evaporation. So condensation, of course, creating the liquid phase, and evaporation, of course, creating the solid phase. And we get to this state of equilibrium where the rate at which, so the speed at which a condensation process is occurring is going to be the exact same speed at which the evaporation state is occurring. And here's your first lecture question for this particular section. Go ahead and pause the screen and answer this. And when you're done, go ahead and play and keep moving on. All right, so then we're going to move on to equilibrium vapor pressure. So we're going to look at this idea of equilibrium applied to vapors, specifically at pressures of our choosing. And so what we're going to see is that molecules that are at a vapor stage are going to be equilibrium with a liquid in a closed system. And when that happens, when we create gases, remember that gases, when they collide with their containers, create pressure. So we're looking at the pressure that's going to be created by a vapor when that vapor is in equilibrium with the liquid it is in contact with at a specific temperature. And we're going to create a curve of this. Now, this equilibrium vapor pressure curve is one you've seen before, but what these do is actually give us information about boiling points. So that boiling point, of course, being when a liquid can become a gas. That is exactly what a boiling point is. And so those of you that answered that, some of you got it right, some of us didn't, but a normal boiling point was what we were looking for when it comes to a vapor pressure curve. So what happens to our vapor pressure is that those are going to go up as our temperatures also go up. So if we talk about a system where we can control pressure and temperature, again, not our environment. We have to create this artificial environment to look at this vapor pressure idea. But if we look at an environment where we can control the pressure, so if we increase the pressure in a vessel, and then we also monitor the temperature, we'll see that as the vapor pressure increases, so will then the temperature of the liquid or the molecules. And just to give you an idea of how this is, there's this lovely picture in your book of what happens with a vapor pressure. This is in advance of your vapor pressure curve. Your version looks slightly different, and it is on page 331, but you look at what's happening in a vessel where we put some molecules and we examine exactly what's happening at equilibrium. Our molecules are going to vaporize, as you see in diagram 3. At the same time, they're also going to condense, and that's what you see in phase 4. Or in number 4, okay? So from there, we can talk about every liquid being different. So some liquids are going to be easier to create our vapor than others, and those are considered volatile liquids. So if it isn't a liquid that evaporates really easily, we call them volatile. Now, you can do this experiment at home. Put some water on your countertop, and then if you have either nail polish remover or isopropyl alcohol, you can put a drop of that right next to it, and you can watch them both evaporate. And one of them will obviously evaporate quicker than the other. Regardless of the temperature, that is this idea of volatility. Now, looking at that alcohol or that acetone, those are going to evaporate first. Now, it may take a little while to monitor, but you can do this yourself at home. And what that is that it means the liquid that evaporates faster, so the volatile liquid, has weaker forces of attraction between them. So less intermolecular attractions, if you will. Okay. Non-volatile liquids, which is most liquids, do not evaporate as easily. Now, a lot of the time, our liquids in our environment, specifically water, take a little longer to evaporate, but that can be sped up by doing what? Increasing the temperature. So in the summer when it rains, the rain evaporates very fast. Because it does that, it's not as effective when it rains in the summer as it is when it rains in the spring for things like our crops. And those non-volatile liquids tend to have stronger forces of attraction because in order to evaporate, you have to overcome the energy keeping you attached to your neighboring molecule. Okay, and we'll talk about that energy a lot when we talk about boiling, but boiling specifically is going to just be another phase change where we go from a liquid to a gas, and the boiling point of a liquid is going to be the temperature where the liquid is at a certain pressure and it is at a certain vapor pressure. So an atmospheric pressure versus vapor pressure. And this is one of those things, those of you that are my bakers, if you look at your baking instructions on, say, just like a box of cake mix, you'll see that if you live at a certain altitude, you should bake at a different temperature or for longer, etc. That's because of atmospheric pressure. If your atmospheric pressure is lower, you're going to see that that baking or that boiling process is going to happen at a lower temperature. So pressure, temperature, directly related. We've seen this before. We've seen this in our gases chapter when we were analyzing the different gas laws. So as pressure goes up, temperature has to go up. As pressure goes down, temperature also has to go down. And this is going to apply to our phases just the same as it did to our gases. Now at the boiling point, and this is the same thing I just said with our condensation or evaporation, in order to change phase, at the molecular level, we have to change the energy that is happening. So in other words, if we have our liquid held at one energy, also known as one temperature, remember temperature and kinetic energy are the same, then we can increase that energy, and when increasing that energy, we're increasing the temperature of our particles, and by increasing the energy in those particles, we're getting them to move faster, and eventually they break away. Okay? Now, pressure obviously also will have an impact here. For our purposes, we just want to make sure that we're understanding what happens at like even pressure. Now, sometimes we may have a pressure above a liquid that is going to be increased. When that happens, the temperature of the liquid has to increase as well. Remember, pressure, temperature, directly related. And that will then change the vapor pressure, which means we have a new boiling point. And the normal boiling point is the thing that we typically refer to. Normal, in this case, actually just relates to the pressure at which the thing is found. So since we live in 1 atm, we call the normal atmospheric pressure 1 atmosphere, and the normal boiling point of any substance is going to be the temperature at which it crosses that 1 atmosphere axis. So remember, these are our vapor pressure curves. You've seen this before. We have pressure on the Y, we have temperature on the X, and we know that the normal boiling point for water, if we're at sea level, 1 atmosphere, is going to be 100 degrees Celsius. We know that the normal boiling point for ethanol and diethyl ether, because we've tested these substances, all of them, at different pressures from 0 atm up to 1. Remember, 760 torr is 1 atm, is 101.3 kilopascals, reminding you of all of the pressure units from our next chapter, technically chapter 11. Those normal boiling points are what we actually see when we change the pressure. So if I said, hey, what's the pressure at 400 torr, you could draw a line all the way over and you could tell me that the boiling point is now lower than it would have been if we were at 1 atm for every single substance, right? Which makes sense, because if we lower the pressure, the boiling point or the change of phase should happen at a lower temperature. Okay? Pressure, temperature, directly related, excuse me. All right, that brings us to the molar enthalpy of vaporization. Now, we did some math this week with specific heat, and that specific heat stuff is going to come back to us in later chapters. But for now, the molar enthalpy of vaporization is kind of like the in-between specific heat problem. So in other words, this is the amount of energy that we can get out of the actual phase change. So if it says molar enthalpy, that implies the heat in a form of energy in the form of heat, and then vaporization is of that actual phase change. So the heat of vaporization is what this is. The energy required to vaporize a liquid at a liquid boiling point, depending on whatever the liquid is. Obviously, this is not the same for every liquid. This changes when the liquid intermolecular attractions also change. So in other words, if we're talking about water versus ethanol or versus that isopropyl alcohol, we know a volatile liquid will evaporate quickly, and we know a liquid like water, which has stronger intermolecular attractions, doesn't evaporate as fast. So the stronger attraction means a higher energy required to break apart the bonds. So in other words, water will require a higher molar enthalpy of vaporization because it has stronger attractions, versus our ethanol, which has fewer attractions. So our alcohols all have weaker intermolecular attractions, if you will, and those weaker intermolecular attractions lead to a lower molar enthalpy of vaporization, or a lower amount of energy needed to vaporize that particular thing. That's why they vaporize in the first place. Okay. All right, so each liquid is going to have some molar enthalpy. Everything is different. Every liquid is made differently. Every interaction is different depending on the shape of the molecules, the distribution of the atoms in the molecules, etc. So water has this weirdly large amount of energy required to vaporize, and that's because of the hydrogen bonding, aka one of the strongest intermolecular forces there are. Now, other things might not have that, and in those cases, those things actually get to escape a lot easier. Which brings us into freezing and melting. So we're going to talk about these two phase changes. Freezing obviously happens when a liquid is becoming a solid, and melting obviously happens when a solid is becoming a liquid. So these two phases are considered similar in that they kind of go opposite directions between the same two phases. So you know what freezing is. You know that freezing is going to involve losing energy. So particles in the liquid phase have to become particles in a solid phase. To go from liquid to solid, we need the molecules to slow down. And to slow molecules down, we remove kinetic energy until they stop moving the way they've been moving in a liquid phase. This is going to occur at a constant temperature. And there's a lot of reasons for that. That constant temperature thing that you see. All phase changes occur at a constant temperature for pure substances like water, like salt, like mercury, like anything you can think of that's a pure substance. So something that isn't considered contaminated or something that doesn't have multiple different molecules in it. Our pure substances will have phase changes that occur at constant temperature, primarily because in order for the thing to be considered in a new phase, it has to convert all of the molecules in the original phase to the new phase before the temperature of all of the molecules can actually change. Okay? This has to do with the impact of molecules on neighboring molecules. So all of the solid molecules, or all of the liquid molecules, in order for freezing to occur, have to release the energy required to become the solid phase before the solid phase can get even colder, right? Because when we're going from liquid to solid, we're obviously losing temperature, which means we're also losing kinetic energy. Now, at the freezing point, if you just stick a probe in there and you try to figure out what the freezing point is, what temperature they're at, you're going to see that you may get different values, but all in all, they are all technically at the same kinetic energy if you average them out. Now, when you reverse the process, you're going to see that instead of having to remove energy, we have to add energy. Again, all going to happen at constant temperature. And I'm going to give you a second here to describe why. You may need to do some reading back in your chapter to discover the answer in a little bit more depth. But for now, understand this all has to do with kinetic energy. In order to go from one phase to another, we're stuck at the phase change for a little while. And at the phase change, we're trying to convert all of the particles to a new phase, whether that be solid to liquid, liquid to solid, solid to gas, gas to solid, whatever that phase change is. In order for it to complete and change temperature, all of the molecules of that particular substance have to have their energy changed. Whether that means they have to have their energy lowered or they have to have their energy increased because we have to put energy in to heat them up, etc., etc. Doesn't matter which phase you're talking about or which change you're talking about, we have to see a change in phase related to kinetic energy change. Okay? Now, if you're talking about, say, melting something, think about the ice outside. I know it snowed last night. In order for the ground to change its specific temperature, all of that ice has to be converted to liquid first, and then you can continue to add energy and change the overall temperature of what remains. So again, all of our phase changes happen at a constant temperature until everything has changed its kinetic energy so that a new temperature can occur, right? And that brings me to this question. Again, if you need to, you can go back and you can reference your materials that you have already looked at, but I want to know why the temperature of a substance does not increase as a solid is melting or as any kind of phase change is occurring. You can go ahead and pause it. When you're done, go ahead and hit play again and we'll move on. All right, so then we have to just discuss real quick the molar enthalpy of fusion. The exact same thing as vaporization, except we're talking about a different phase change. Fusion, of course, implies the amount of energy required to melt a solid. Now, this is going to relate to 1 mole specifically. That's the term molar in there. Enthalpy is heat or energy, and fusion is the phase change itself. Now, again, this is an amount of energy at a specific phase change. There are molar enthalpies of fusion, vaporization, condensation, freezing, melting. I mean, there are all kinds of molar enthalpies to discuss. For us, we're just going to focus on fusion, and we're going to focus on vaporization in this chapter. Last phase changes we want to talk about are sublimation and deposition. More rare, because these have to happen at specific temperature and pressure conditions. A lot more this happens at low temperatures and lower pressures, lower than the triple point, if you will. When we look at our phase diagram here in a minute, we'll see exactly where sublimation has to occur, but very specific conditions have to occur for sublimation and deposition. So sublimation is going to be the change of state from a solid to a gas. Remember, it happens at a constant temperature, and our reverse process where we take a gas and we make it a solid is called deposition, and that is going to be that change of state from a gas directly to a solid. All right, that brings us to understanding phase diagrams. So on our right here, we see at the top the phase diagram for water, and at the bottom, this is the phase diagram for carbon dioxide. Couple of things you might notice. Water is weird. We've said it 100 times. I'm going to continue to say it. Up here at the top of this diagram, the reason that water is weird, according to from a phase diagram sense, this line bends backward. Almost every single other substance we know of has that line bend forward. So it's very, very different. And when we were talking about the different phase changes, we have the 3 different phases on every single diagram. They are very much all the same as far as phase diagrams are concerned. Regardless of the phase diagram you are given, as long as it has pressure on the Y, temperature on the X, then you can be very, very confident that you're going to have solid on the left, liquid on the top, gas on the bottom. Okay? And you can see those red lines. What do those red lines represent in your opinion? Hopefully you're going to say the transition phase. So our phase from liquid to vapor, in other words, our evaporation going from liquid to vapor, has to happen at this specific line. So let's say we're at a pressure of 1 atm. At this line is where the actual phase change is going to occur, and at this temperature is where that will actually happen, or et cetera, et cetera. So if we're talking about starting in one phase and moving to another, we know that it's going to happen when you cross that red line. You're going to see that phase change occurs, whatever the phase change is. Sometimes you can use these to actually locate where, what phase something would be in at specific conditions. So if I asked you what the phase of water would be at 1 atmosphere and 50 degrees Celsius, you would follow that 1 atmosphere, put me somewhere in here, and you'd be like, oh, that's liquid. That's easy, right? That is exactly how you read these phase diagrams. Now, these are going to have a few more pieces of information which you've already actually investigated. One is going to be the triple point. The triple point of a substance is considered the point at which all 3 phases exists at the same time. And if we were in class, I'd be showing you a really cool video of cyclohexane at the triple point. You can look it up yourself if you like on YouTube, but cyclohexane at its triple point is actually really cool. You can also look up the critical point. You can find several YouTube videos out there of different substances at their critical and triple points. At the critical point, we see that we start to kind of lose a sense of vapor or liquid. You know, we kind of play this game at the critical point and above the critical point. So top, keep going up, extend the graph up. We play this game of what phase is it? And the answer is both at the same time. We call it a supercritical fluid. So after that critical point, above that critical point, as far as pressure and temperature is concerned, we start to see this like discombobity of, is it a liquid? Is it a gas? You could play the game of I have no idea. And that's okay. The critical temperature and pressure are going to be exactly what you think. They're going to be considered the temperature where certain things are going to happen. So a critical temperature is the temperature where a substance can't exist in the liquid state any longer. So any point above that temperature, that substance can't be a liquid. It can't be liquefied no matter what you do to it. You can't change it. I mean, changing the pressure doesn't do much. Above that temperature, you're just going to not see liquid water anymore. The critical pressure, again, something similar. The lowest pressure where the substance can exist is a liquid. Critical temperature, okay? They are, of course, linked. All right, and this is your next question. Just describe the important features of a phase diagram. So draw a phase diagram in your question, answer, and show me exactly what the different things mean. So what do the red lines mean, or what do the lines mean? Where are the different phases located? What is a triple point? What is a critical point? Where is the supercritical fluid located? Go ahead and pause and do this question, and when you're done, come back and we will continue. We have one more slide. Last slide, and that is just the phases of change. I love this diagram. This diagram is in your book, and I highly recommend that you study it if you're still not really familiar what your phase changes are. Some of you are like, oh, this is easy. I've been studying this stuff since I was in 7th or 8th grade. Great. Some of you are like, I don't have any idea what a deposition is, and that's okay. I'd like you to know these changes of state, and I'd like you to know which state they go from and to. This kind of stuff will be questions that are asked on your quiz. That will be emailed out on Wednesday. Right, and that is the end of our lecture.